This is Jack Jackson, and we have another video in our series here, the 18th one in this series of videos talking about the derivative and defining it and understanding some basic properties and concepts relating to it. This particular one is going to be about finding the formula of the derivative function of another function via the definition. So later on we'll learn some shortcuts to this, but at this point we want to use the actual definition. So we had looked at this earlier, and we said f of x is x squared. In an earlier video we used our estimation techniques to find the derivative at several points, or approximate the derivative at several points, and we figured out that from the table of values that we derived that it looked like the formula for f prime of x was just the formula 2x. Now let's see if we can actually prove that formally and derive that formally. So to do that, we need to use the definition of the derivative. So here's the definition of the derivative. F prime of x is, by definition, the limit as h approaches 0 of f of x plus h minus f of x over h. Now our particular formula is y equals x squared. So when it says f of x, this part, right, so you want to think of this part being what goes in this parentheses, which is just our original function f of x, x squared. What goes here in this part right here is this f. Let me put just another parentheses around it. So what goes in that parentheses is the original function evaluated at x plus h. So you plug x plus h in place of x in the formula. In this case, the formula is take input and square it. The input is x plus h. We square it. Notice that f of x plus h is not the same thing as f of x and then plus h. So let me just write that out by hand here. So things to watch out for. F of x plus h is not f of x plus f of h. And it's also not f of x and then just add h to it. What it is you take x plus h as the input for the formula. So if f of x is x squared, f of x plus h, you would take where the x is, put a parentheses like that, and in that parentheses put the x plus h. So that's what I've done here. Okay, so let's take this and see what we can do with it. Okay, so I don't really need that parentheses. Let's get rid of it. So what we have here is this x plus h squared. Well, x plus h times x plus h is, turns out to be x squared plus h squared. But it's not just x squared plus h squared. You have the middle term. It's 2hx. And that replaces this part right here. So x squared plus 2hx plus h squared. If you want to think of that, it's the distributive property, sometimes known by the anagram FOIL, F-O-I-L. First times first, x times x is x squared. L is last times last, h times h is h squared. And the O and the I stand for inner and outer product, which are both x times h, and there are two of them added up to be 2x, 2 times h times x. Now, so we expand that out, and then what we want to do here is look at this and see if we can do any simplification. Do you see anything we could do here? Well, if you notice, that minus x squared and that plus x squared cancel each other out. Now what can we do? Now, by the way, notice when we're doing this limit, if we let h be equal to 0 at the beginning, x plus 0 is 0, f of x minus f of x is 0 over 0. It's 0 over 0 every single time, and that's going to be true if you plug in h as 0 in any of these expressions as we go down. So the basic way we do this is plug in the formula here and look at the difference quotient part. Forget the limit, just leave it alone for the ride, and work with the algebra here in this fraction. And what we want to do is see if we can simplify this a little bit. And you see anything else that we can do? Well, hopefully you see that in the numerator we can take this and factor this factor an h out of this, which means what's left in here, we're dividing both of these by h, so that puts that down to the first power, and it gets rid of this h altogether. Now we use the property of fractions that says that these h's cancel out, and that only leaves this part 2x plus h over 1. So we could write it like that, for example, and that h over h is 1, so that cancels. Remember, h is not 0. As long as h is not 0, these are the same. Now this one is continuous at h, so if we can actually just plug in the h as 0. So notice up to this point we haven't actually taken the limit. Okay, but at this point we can actually take the limit of each piece, and that actually goes to 0, and then as we suspected, the final answer is f prime of x equals 2x. So notice the basic way we have to go at this to actually find an actual formula for the derivative. You have to look at the definition here, which is f of x plus h minus f of x over h, and take the limit as h goes to 0. How many times have I said that in this series of videos? Many, many, many times. Very important that we understand that and memorize that definition. So now plug it in. In this case here, on the second part after the subtraction, in the second parentheses, this right here is just f of x. It's your original formula. This other set of parentheses is f of x, but instead of, it's f of x plus h. So you take your original formula, in place of the x you put x plus h. Then you simplify any way you can. So in this case we expand this out, combine like terms, and typically this is what happens. The stuff without the h's cancels out. So when you're left with everything in the numerator just has all of it has an h in it. So then we can factor the h out, which allows us to cancel the h's, and once those h's cancel out, now we can evaluate the limit by basically just plugging in the h is 0. We're actually using a couple of limit properties. The limit of the sum is the sum of the limits, and this one doesn't have an h, so it might as well be considered a constant. And so the limit of that constant is just 2x, and as h goes to 0, of course that goes to 0, and we get 2x for our answer. So basically, a whole bunch of algebra steps and 2 calculus steps. First calculus step is knowing the limit that defines the derivative at the beginning, and then the calculus step, the real easy calculus step right here at the end, when we evaluate the limit right at the end. A whole bunch of algebra steps in between. Let's do another. Oh, before we do that, let's go over a way that we could actually check this on our calculators. Think about how we could do this. Well, so here's a TI-84 version of a check. Well, this is for a different function here. Okay, actually, let me get rid of this. Let me actually show you how to check this on a TI-84. So give me a second to pull up my TI-84 emulator, and let's think about how we could do this while this is loading up. Remember, we can graph the symmetric difference quotient or compute a table for the symmetric difference quotient, and because of that we can get an approximation of a derivative. So if we put our original formula y equals x squared in y1, we can get a numerical derivative approximating that, in other words a symmetric difference quotient approximating that in y2. And if you remember, that was math number 8, which is a numerical derivative, math 8. And if you have the newer operating system, it looks like this. It looks like Leibniz notation. So we do an x there. We refer back to the function y1. That's a short way to get it. The old way, the old way to do it is this, which works on all the TI-84s or 83s. You hit variables, right arrow to y variables, select function y1. And then this would be your a value, the value where you're evaluating it, but instead of putting in a specific number, we're going to put in the variable x. So this makes it the derivative function, essentially, here, and we looked at this in an earlier video. Now, to check that, we can put the formula that we came up with, which is y equals 2x. Now we can actually go up here and turn off but not delete y1. So y1 will not show up in our table or our graph like that. Now notice you can actually leave y2 and turn it on or off as needed like we did here. Just leave it for the whole course because that will find the derivative, numerical derivative, the symmetric difference quotient of y1. The actual derivative that we came up with is 2x there. And now if we do a table for these two, we should see that they match up. Let me just do some sort of table here. Maybe let's start at -3 and go up by 1s automatically. Delta x is 1. And then look at the table, and these should be the same number. Now, in some cases, they may be just slightly off, and if the one in y3, if we did it correctly, is the exact value, and the one in y2 is the approximate, but if they all round off to the same thing, we feel pretty good that we have the right answer. Okay, so let's go back and let me just pull these screenshots over here. Okay, and so you can see what these look like. So if you can get those tables to be the same, then in fact we have checked it. So you can always check your derivative formulas this way with the TI-84 or TI-83. It won't compute the derivative formula for you. A TI-Inspire CAS, for example, or a TI-89 would do that. But you can do on a TI-Inspire non-CAS, a TI-83, a TI-82, TI-84, for example. All of those you can check your derivative problems this way. Okay, let's do another example. F of x equals 3x squared minus 2x plus 7. Okay, we'll get to that in a minute. So here we have our function. So basically we're going to have two sets of parentheses here, like this, and we have to put in those two parentheses something. Well, the second one is f of x, so it's just our original formula. The first one, you put the same thing here, except everywhere there is an x, we're going to replace it with a parentheses with x plus h in that parentheses. And so there is the derivative. Now we just got to simplify it a little bit. Okay. So there's our one of two calculus steps. Now we want to work this out. I'm going to start by expanding this part right here out. Okay, so x plus h squared is x squared plus 2hx plus h squared. Alright, that's that step. Do the powers first. Now let's see, now we can do some distributing. So we want to take this part right here, let me move it out here, and we're going to multiply each part by 3. So that's going to be 3 there. This is going to become 6. That's going to become 3. So this is gone. We're going to take the x plus h and we're going to multiply it by -2. There and there. So that takes care of that. And the last part is just plus 7. Okay, and then we're going to distribute this minus. So that becomes minus 3x squared. Then we get plus 2x and minus 7. Alright, well, we've expanded that all out. Now, next comes the fun part because some things start to disappear. This minus 7 and this plus 7 cancel each other out. The 2x and the minus 2x cancel each other out. The minus 3x squared and the plus 3x squared cancel each other out. Okay, things are starting to look a lot better now. Now, if you've done this right, what should happen at some point along the way here is what you have left in the numerator, all of it has a factor of h. So we should be able to factor the h out of this. And of course, when I factor the h out, I'm dividing each of these terms by h. That goes down to no h's. That goes down to h the first power. The h disappears there. So we're at that point. Next, we cancel the h's out. So a whole bunch of algebra steps here. Okay, canceling the h's out only leaves us this part right here, and the h over h is there, which cancels out to be 1. So that's gone. And now we get to our second calculus step, which is we take this formula here, and I guess we're doing technically we're doing 2 or 3 limit rules here. The limit of each piece, and then factor the constants out, and basically we can just substitute in 0 for h at this point. And if we work that out, this term goes away to 0, so that's gone. And so our formula is 6x minus 2. Okay, let's go ahead and check it again. 3x squared minus 2x plus 7. Get rid of that square. There we go. 3x squared minus 2x plus 7. There we go. And leave that the same, and then in y2 is set up the same. In fact, we can toggle off y1 so it won't show up in our table, so we don't actually accidentally try to compare y1 and y2. We're only going to show up y2 and y3. And the answer was 6x minus 2. Is that what we came up with? Yep, 6, see it out there? 6x minus 2. And if we did that right, here we go. Look at the tables. Yep, they match up. So they check. Okay, so we get a nice screenshot there. And we've done that one. So let's try another one. Let's do 1 over x this time. So again, we just have a parentheses here and here like that, right? So the second parentheses, we just put in the original function, 1 over x. The first set of parentheses, we put in the original function, but instead of x, we put x minus h there. Now we're thinking of that. This is optional, but we might put parentheses there. There's our calculus step. Alright, let's do some algebra steps. Think of the top here as one. Let's do it like this. Hold on. The problem with this, it looks kind of messy. Why? Because we have fractions inside the fractions. Okay, we think back to elementary school, how we dealt with that problem, or in our intermediate algebra problem, how we dealt with that. We find a common denominator of all the little denominators. Think of this as h over 1, 1 over x minus h, 1 over x. We want to find the common denominator of all those, which is x times an x minus h. And if we will multiply the top and bottom of this fraction by that, then we get an equivalent expression. Okay, provided neither one of these things is 0. Okay, if x is 0, 1 over x is undefined anyway, so that's not a problem. And the only way to make x minus h 0 is would be if x is h. So, okay, so let's try that. Alright, now down here we distribute. So when we distribute this part right here by this, the x minus h cancels and we're left with an x. The next time when you multiply this, you're left with the x cancels and you're left with x minus h. So the top just turns out to be that. Look at that again. So you take the x minus h times the 1 over x minus h. The x minus h is canceled. You get the x times the 1 is x. Next you take a fresh x times x minus h times this one. This is the distributive property we're using. The x is canceled. You got negative 1 times x minus h is what I have here. And I'm just going to leave it in the bottom the same way. I don't need this parentheses here, so I'm just going to write it like that. But otherwise the same thing. Now I'm going to use the distributive property again and make this, distribute this minus 1, and so this becomes minus x and then plus h. Now the x minus x's cancel, and so we're just left with an h in the top. Hey, look at that. Once again, we can now finally get down to where we cancel those h's out. That h over h was our problem. Up until this point we get 0 divided by 0. But we can cancel that out, leaving a 1 there, and that's gone. Now at this point we can actually compute the limit. So notice that limit sign has been there all along. Now the limit goes away when we let that h actually just go to 0, and this becomes x, and x times x is x squared. So I can just write this 1 over x squared. Again, let's just check it with our calculator. So get used to doing that every time. Okay, all we have to do is go back and change the formulas. And y1 is the original formula, 1 over x, which we can actually toggle off so that it doesn't show up in the graph or the table. And then y2 is our numerical derivative, which notice I haven't had to change. And then this is the answer, 1 divided by x squared is our actual answer, our actual function there for the derivative. And then we can graph that. Or actually we could graph it and the two graphs should be on top of each other. It's a little hard to tell just looking at it if they're actually on top of each other or one's off the screen. So it's actually easier to test if you just look at the table. And we see that. Notice actually something interesting is happening, and I think this is something that I kind of pointed out earlier, or said something about earlier. Notice that we get an error message on the derivative. 1 over x squared is undefined when x is 0. Of course, the original function 1 over x is undefined when x is 0, so it makes sense that the derivative should also be undefined there, and sure enough it is. But notice the symmetric difference quotient actually came up with some kind of number there for using a symmetric difference quotient, some kind of number, which may or not make any sense. Okay, in this case it doesn't make any sense. So that was actually just an error there, something the calculator said that was wrong. But if we go up to something like this, notice the symmetric difference quotient said was negative point, oh, how many? 1, 1, 1, 1, 1, 1, 1, 2, 3, 4, 6. The actual value is negative, is 0.1. Oh, something's wrong here. We lost a sign. Okay, we made a mistake back here. Let's fix it. Where did we drop a sign? Right. Where? Oh, this should be x plus h right here. There it is. X plus h. X plus h. There we go. Okay, and then when you distribute the negative, that's minus. Then when this is, so this is minus h, when you, this gets to be minus 1. And this is minus 1. And so this becomes negative 1 over x squared. Aha! That's better. That's the right answer. And we see that now when we try to check it. So as you see the value of doing a check, you can catch a little mistake like that. Okay. Okay. So that should be the right one. Now let's see if that works out better. So now we look at our table, and now look what we got. Okay, so again we get negative 0.11111112346. The actual value is negative 0.1 repeating, negative 1/9 when we plug in negative 3. And of course that's, if you plug in negative 3 squared is 9, negative 1 over 9 is negative 1/9. In decimals that's negative 0.1 repeating. So notice that the values in y3, now that we made the correction, are actually the correct values, and in y2 those are approximations. But they're approximately the same, and so that tells us that now that we made our fix, that these are actually, that we actually now have the correct answer. So you can see the value in checking a problem like that. Now we know we have the right answer. One more. F of x equals 5x cubed. So once again, it always looks like this. Like this. And here we put in the original formula, 5x cubed. In the first one we take that formula, but in place of it we put in x plus h. I don't know why I did x minus h last time, but x plus h, like that. Now we need to work this out. Let me go out. Let me do some scratch work on the side here a minute. If you have x plus h times x plus h, and you're multiplying, you go h times h is h squared. This is xh. This is h times x. This is xh. This is x squared. So this is x squared plus 2xh plus h squared. So this is x plus h squared. Now if we multiply by another x plus h, we get h cubed plus 2xh squared plus x squared h. And if x times h squared is xh squared. Notice I'm lining up like terms. Multiply these two together, we get 2x squared h. And then this is x cubed. So we add those together. Notice we do get an x cubed and we do get an h cubed, but this time we get two middle terms, 3x square h and 3xh squared. Okay, so that is x plus h cubed. Okay, so let's put that in here. So in this part we get, okay, if we remember what it was x cubed plus 3x square h plus 3xh squared plus h cubed. So that's cubing that out. Alright, so what do we get here? Now we take this right here and we're going to distribute it 5. So we're going to multiply each term by 5. So this is 5x cubed plus 15x square h plus 15xh squared plus 5h cubed. And the last one we just distribute or just multiply by the -1 and we get negative 5x cubed. Now what changes here? Well, this part cancels with this part. Hey, look at it. Look at that. Once again, all the things at the top have an h. So what's the next step? Factor an h out. Okay, we factor an h out of this. What are we left with? We have to divide each of these terms by h. So that h goes away. This h goes down to first power, and this one goes away. I'm sorry, no cubed anymore. Sorry. It was an h cubed, but we cancel one of them, so it goes down to square. There we go. That's right. Now we see the h in the top and bottom as factors. We can cancel that out. And so that part's gone, and we're just left with this h over h cancels. Now, use our limit laws. Now finally we get back to a calculus step again after all those algebra steps. And it says, using our limit laws, we actually take the limit. Up to this point, the limit's just been along for the ride by actually putting in a 0 in place of the h's. And it's okay at this point because our limit laws tell us essentially that that's going to work. These terms are all 0, so everything cancels out except for the 15x squared. Alright, let's check it, make sure we didn't make any mistakes there. Okay, check it with the calculator. Okay, so y1 is your original function, 5x cubed. Again, we can turn that off so we don't have to mess with it in the table. Can't delete it, of course. Y2 depends on it. Y2 is the symmetric difference quotient, the numerical derivative. Y3 was our answer, which was 15x squared. Is that what we got? So down here again. Yep, 15x squared. And now, hopefully that's right. Okay, and let's see what happens when we look at our table. Here's the moment of truth. Does it check out? Hey, look at that. It checks out. All the things are checking out. That's not exactly 135. It's 135.000005. The actual answer, as we see, is really 135 exactly. Okay, but that's approximately the same, so that checks out. This one here may look a little different. That's 5e negative 6. That means 5 times 10 to the negative 6. So that's 0.00000, 5 zeros, and then a 5, which is practically 0. The actual answer is, the derivative is actually 0. So again, those are approximately the same. And I can scroll up and down the table a little bit more if I wanted to check some more. But that's going to be sufficient, I think, to convince me that I did the right thing. And so, you've seen several of examples of how to go about finding the derivative formula. Now, of course, once I found the derivative formula, how could I find the exact value of the derivative of this thing at 7? Okay, well, we estimated it with a table early on. We estimated it by looking at the graph. We estimated it with numerical derivative, a symmetric difference quotient, but we can find the exact value by using this process to find the formula for the derivative, okay, which was, what was it, 15x squared, and then if we want to, we just plug in 7. 7 squared is 49, and we just do 49 times 15. You can see that here in the table by just going down to 7 in the table, and we see that that's 735. And so that's how you can find exact values of the derivative, and you can find the exact value for the formula of the derivative function.